Module 29, Lecture A, Classification Metrics. By the end of this lecture, you will be able to use built-in and custom scores for classification evaluation, compute and interpret threshold-based and probability-based classification metrics, and evaluate multiclass, multilabel, ranking, and top K classification outputs. Scorer API. Available scorer names. In classification evaluation, a scorer name tells a machine learning library which metric to use, such as accuracy or recall. This makes it easy to apply the same measure during tasks like cross-validation or hyperparameter tuning. Different scorer names reflect different goals, such as using accuracy for balanced data or recall when missing true cases is especially costly. Machine learning scorers reflect what kind of prediction output an evaluation needs. Measures like accuracy and F1 compare predicted class labels with true labels, while area under the curve uses confidence scores to judge how well a model ranks cases before a threshold is chosen. The right score should match the problem and the cost of errors, so evaluation supports the real-world goal. Choose scoring measures that match the structure and goals of your classification problem. In binary classification, make sure the positive class reflects what you care about most. For multiclass or imbalanced data, use measures such as balanced accuracy or macro averages to avoid hiding poor performance on rare classes. The best scorer connects model evaluation to the real-world errors and outcomes that matter. Python code. Available scorer names. This script shows the available scorer names for classification tasks. These names provide a standard way to choose model evaluation metrics, including scores based on predicted labels and predicted probabilities. We import Scikit-Learn and use its metrics tools to access the available scorer names. This gives us the standardized scoring methods used to evaluate machine learning models. Scikit-Learn provides a built-in way to retrieve all available model scoring names from its metrics module. Sorting these names alphabetically makes them easier to browse and use. This list acts as a standard vocabulary for consistent model evaluation. The code defines a beginner-friendly set of classification metrics, including accuracy, balanced accuracy, precision, recall, F1 score, ROC AUC, and average precision. Together, these scores assess performance using both predicted class labels and predicted probabilities, giving a broader view of how well a model works. This code defines a group of label-based classification metrics, including accuracy, balanced accuracy, precision, recall, and F1 score. These metrics judge a model by comparing its final predicted class labels with the true classes. This defines a group of score-based evaluation measures, including ROC AUC and average precision. These measures use model scores or predicted probabilities instead of final class labels, helping assess how well a model ranks or estimates outcomes. We check whether any selected scorer names are missing from the library's available scorers. If any are missing, we raise a value error to stop the process and alert us that the chosen scorer names are invalid. This safeguard helps prevent problems during model evaluation. The script checks the Scikit-Learn version, shows how many built-in scoring metrics are available, and gives examples of scorers based on predicted labels or predicted probabilities. Label-based scorers include measures like accuracy and precision, while probability-based scorers include metrics such as area under the ROC curve. When choosing a scoring option for model selection, use the exact scorer names provided by Scikit-Learn to ensure correct evaluation. This script shows which classification scores are available in Scikit-Learn and highlights beginner-friendly options. It separates scorers that use predicted class labels, such as accuracy and precision, from those that use prediction scores or probabilities, such as the area under the ROC curve. It also checks that the selected scorer names exist in the installed Scikit-Learn version, helping you use the correct strings for model evaluation. Custom scorer functions. Custom scorer functions are useful when standard metrics like accuracy or precision do not reflect what matters most in a classification task. They translate model predictions into a performance score that matches real priorities, such as emphasizing missed high-risk patients in healthcare or balancing false alarms and missed fraud in fraud detection. This helps model selection and tuning focus on the outcomes that are most important for the problem. When creating a custom scorer, choose a metric based on the true labels and the model outputs it can provide, such as class predictions or probabilities. Make sure the scorer matches the type of output available, since probability-based scoring will not work with models that only return labels. Also define whether higher scores mean better performance, converting error measures if needed, so model comparisons remain consistent during tasks like cross-validation. Custom scorers must be validated carefully because they can strongly affect which model seems best. A good scorer should be transparent, stable, and aligned with the real decisions the model supports. Testing it on simple cases helps confirm that it responds correctly as predictions change. In machine learning, custom scoring makes evaluation more relevant by reflecting domain-specific values and constraints. Python code custom scorer functions. This example creates a custom classification score that values recall more than precision. Cross-validation is then used to compare standard accuracy with this custom scoring approach. This setup imports the main Scikit-Learn tools needed to build and evaluate a binary classifier on the breast cancer dataset. It uses logistic regression as the model, standard scaling to normalize the features, and a pipeline to combine pre-processing with modeling. For evaluation, it uses stratified cross-validation to keep class proportions balanced across folds, along with recall as the scoring measure to assess how well the classifier finds positive cases. We load Scikit-Learn's breast cancer dataset, a standard dataset for binary classification. The data is separated into input features and target labels, so the model has clear information to learn from and a defined outcome to predict. Before training, the code verifies that the feature data and target labels have the same number of entries. This ensures every data point has a matching label. If they do not align, it raises an error to prevent problems during model training. We build a simple modeling pipeline that first standardizes the input features by centering them and scaling them to unit variance. This helps logistic regression work reliably when feature scales differ. The pipeline then fits a logistic regression model using enough iterations for convergence and a fixed random state for reproducible results. Together, these steps combine pre-processing and modeling into one streamlined workflow. The high recall score function evaluates a classifier by calculating recall for the class labeled 0. It compares the true labels with the predicted labels and focuses on how well the model identifies that specific class. This is useful when false negatives are especially costly, because the score emphasizes catching as many relevant cases as possible. We convert the custom high recall metric into a Scikit-Learn scorer using the makeScorer function. This lets Scikit-Learn apply the custom scoring rule during model evaluation and cross-validation. We use stratified 5-fold cross-validation, so each split keeps the same class balance as the full dataset. Each fold serves once as the test set, while the remaining folds train the model. Shuffling adds randomness for a more robust evaluation, and a fixed random state makes the result reproducible. We evaluate the model with cross-validation using accuracy. Then repeat the process with a custom scorer that emphasizes high recall. This lets us compare standard accuracy against a metric focused on finding more positive cases. The code reports the scikit-learn version, then summarizes cross-validation performance using two rounded average scores. Accuracy shows overall prediction correctness, while the custom high-risk recall score focuses on how well the model identifies the positive class. Printing both metrics gives a quick comparison for evaluating and choosing the model. This script shows how to evaluate a scikit-learn classification model with a custom scoring metric. It uses the breast cancer dataset with logistic regression and standard scaling, then compares standard accuracy with a score that emphasizes recall for the negative class. Using fivefold stratified cross-validation, it reports the scikit-learn version, mean accuracy, and mean custom recall score, showing how model performance can look different depending on the evaluation metric. Accuracy variance. Accuracy measures how often a model's predictions match the true labels, making it a simple and common evaluation choice. It works best when classes are balanced and different mistakes have similar costs, such as basic category sorting. However, accuracy is only one scoring option, so it should be used only when it matches the real goals of the application. Balanced accuracy is useful for imbalanced classification because it gives each class equal weight, rather than letting the majority class dominate the score. This matters in settings like medical screening, fraud detection, and safety monitoring, where rare cases may be the most important to catch. Using balanced accuracy can lead to better model choices during tuning, and helps align performance with practical and ethical needs. For multiclass and multilabel tasks, the right form of accuracy depends on what the task needs. Multiclass accuracy usually requires the predicted class to match exactly, while multilabel accuracy may be measured label by label to give credit for partial matches. The Scorer API lets you choose or define the accuracy measure that best reflects your data and the real-world cost of mistakes. Python code, accuracy variance. On imbalanced classification data, different accuracy scores can favor different models. Balanced accuracy gives minority classes fairer weight, so comparing the printed scores helps reveal which model each scoring method prefers. This setup imports key scikit-learn tools for a classification workflow. It includes a function to create a synthetic classification dataset, a dummy classifier for a simple baseline, and logistic regression for a stronger binary classification model. It also brings in accuracy and balanced accuracy measures, a way to retrieve scores by name, and a train test split tool to evaluate models on unseen data. We create a small imbalanced binary classification dataset using scikit-learn's make classification function. It contains 800 samples with 6 features, with about 90% in one class and 10% in the other. A random state of 42 makes the dataset reproducible. The code checks that the label data contains exactly 2 unique classes, which is required for this binary classification task. If it finds any other number of classes, it raises an error to show that the dataset is not suitable for the lesson. We split the dataset into training and testing sets using scikit-learn's train test split function, reserving 30% for testing. Stratifying by the labels keeps the original class imbalance in both sets, which supports a fairer evaluation. A fixed random state makes the split reproducible across runs. We create a simple baseline model using scikit-learn's dummy classifier with the most frequent strategy, so it always predicts the majority class in the training data. After fitting it to the training features and labels, it captures only the class distribution, not real patterns. This gives us a naive benchmark for judging more advanced models on an imbalanced dataset. We create a logistic regression model with a fixed random state for reproducible results and allow up to 500 training iterations. Then we train it on the training data so it can learn the relationship between the features and labels and make predictions on new data. We generate test set predictions from both models so their performance can be compared. The dummy classifier predicts using the most frequent training class, while the logistic regression model uses the patterns it learned during training to make more informed predictions. We create two scorer objects using Scikit-Learn's getScorer function to evaluate models later. The accuracy scorer measures the overall share of correct predictions, while the balanced accuracy scorer gives a fairer view when classes are uneven by considering performance across each class. We evaluate both the baseline and logistic regression models using two metrics. Accuracy shows how often each model predicts the correct test label, while balanced accuracy gives a fairer score when the classes are imbalanced by weighting each class equally. We evaluate the logistic regression model on the test data using two metrics, standard accuracy and balanced accuracy. Standard accuracy measures the overall share of correct predictions, while balanced accuracy gives equal weight to each class, making it useful when classes are imbalanced. Comparing both scores gives a clearer view of the model's performance. We first check the Scikit-Learn version to support reproducibility. Then, review the test set class counts to understand any imbalance. The main comparison reports accuracy and balanced accuracy for both the baseline model and the logistic regression model. Accuracy shows overall correctness, while balanced accuracy gives equal weight to each class. Finally, the same metrics are verified with Scikit-Learn's scorer tools to confirm the results are consistent. This script shows why standard accuracy can be misleading for imbalanced classification. It creates data where most samples belong to one class, then compares a majority class baseline with logistic regression using both standard accuracy and balanced accuracy. The baseline appears strong under standard accuracy because it predicts the dominant class, but its low balanced accuracy reveals poor performance on the minority class. Logistic regression performs more evenly across classes, and the Scorer API confirms the same metric results. Classification metrics: precision, recall, F-score. Precision, recall, and the F-score are important measures for judging classification models, especially when the positive class matters most. Precision shows how often positive predictions are correct, which helps when false alarms are costly. Recall shows how well the model finds all real positive cases, which matters when missed cases are risky. Together, these metrics help evaluate the trade-off between different kinds of errors. Precision and recall depend on how strict a model is when labeling positives. A cautious model usually has higher precision but lower recall because it misses more true positives, while an aggressive model improves recall but creates more false positives. This trade-off is controlled by the classification threshold, so choosing it should depend on the real-world cost of each type of error, not just the metric scores. The F-score combines precision and recall into one measure, giving a more balanced view when both matter. The F1 score weights them equally and is especially useful when accuracy can be misleading, such as with imbalanced data. Still, it is not always the best metric, because some tasks need higher precision, while others need higher recall. For good evaluation, consider precision, recall, the F-score, decision thresholds, and the real impact of different errors together. Python code, precision recall, F-score. This example compares precision, recall, and F-score using fixed labels to show their trade-offs. It highlights how making predictions stricter can improve some scores while lowering others. We import NumPy to work with arrays and check the Scikit-Learn version for reference. We also import the F1 score, precision score, and recall score tools from Scikit-Learn, so we can evaluate model predictions using these key performance metrics. We define the true labels as an array of actual outcomes, where ones mark positive cases and zeros mark negative cases. These labels provide the reference needed to evaluate how well prediction models match the real results. A cautious model's predictions are represented as an array of 10 outcomes, with positive and negative predictions marked separately. It predicts positive only 3 times, showing a conservative strategy meant to reduce false positives. These predictions can be used to compare how different strategies affect precision, recall, and the F1 score. An aggressive model is represented by an array of positive and negative predictions, with more positives included by design. This approach tries to capture as many true positives as possible, but it may also create more false positives. The predictions can then be used to compare its precision, recall, and F1 score with a more cautious model. The code first verifies that the true labels and cautious predictions have matching shapes, so each prediction lines up with the correct label. If they do not match, it raises an error. This check prevents invalid precision, recall, and F1 score calculations caused by misaligned data. First, confirm that the true labels and aggressive predictions have the same shape, so each prediction matches a label. If they do not align, an error is raised. This check helps ensure later metric calculations are valid and accurate. 2 paired lists are created to compare cautious and aggressive prediction styles. One stores the model labels, and the other stores the matching prediction arrays in the same order. This makes it easy to loop through each style and calculate precision, recall, and F1 score for comparison. The code first displays the Scikit-Learn version to support compatibility and reproducibility. It then prints column labels for a results table showing each model's precision, recall, and F1 score, which are standard measures for evaluating classification performance. The code compares several models by looping through their names and predictions together. For each model, it uses Scikit-Learn to calculate precision, recall, and the F1 score while safely handling any division by 0. It then prints these metrics with the model name so the results are easy to compare. The statements compare 2 prediction strategies using precision and recall. The cautious model predicts fewer positives, so it has higher precision and fewer false positives. The aggressive model catches more positives, so it has higher recall and fewer false negatives. Together, these metrics show how each model's behavior affects its performance. This script compares 2 prediction models using precision, recall, and F1 score. The cautious model predicts fewer positives, so it has higher precision but misses more true positives. The aggressive model predicts more positives, so it improves recall but lowers precision. The F1 score summarizes the balance between these 2 measures, showing the trade-off between different prediction strategies. Confusion matrix basics. A confusion matrix helps evaluate a classification model by showing both correct and incorrect predictions. In binary classification, it separates results into true positives, true negatives, false positives, and false negatives, such as correctly detecting fraud or mistakenly flagging a legitimate transaction. This gives a more detailed view than accuracy alone, because different types of errors can have different consequences. A confusion matrix is especially useful when classes are imbalanced or different mistakes have different costs. In rare disease screening, high accuracy can hide missed cases, where false negatives are more serious than false positives. In spam detection, the trade-off is different, since blocking an important email may be worse than letting some spam through. The matrix makes these error trade-offs clearer than accuracy alone. A confusion matrix shows the counts behind threshold-based metrics such as precision and recall. Changing the decision threshold changes the numbers of true and false positives, so the matrix can be used to compare different decision policies, not just report performance. In multiclass problems, it also reveals which categories the model tends to confuse. Python code. Confusion matrix basics. This example creates a simple confusion matrix to show how a model performs. It separates correct predictions from two types of errors, making the printed counts easy to interpret. We import NumPy to handle numerical arrays efficiently, and use Scikit-Learn's metrics tools to evaluate a classification model. In particular, the confusion matrix function compares true labels with predicted labels to summarize model performance. We create two NumPy arrays for a small fraud detection test set, one with the actual outcomes and one with the model's predicted outcomes. Comparing these two arrays lets us evaluate how well the model performed. The code compares true labels with predicted labels to build a 2x2 confusion matrix for classes 0 and 1. It then separates the matrix into true negatives, false positives, false negatives, and true positives, making the model's classification performance easier to interpret. This code checks that the confusion matrix has the correct 2x2 shape for binary classification. If the size is different, it raises an error to prevent invalid analysis. Accuracy measures the share of all predictions that were correct, using both true positives and true negatives. Recall shows how well the model finds actual positive cases by comparing true positives with all real positives. Precision shows how many predicted positives were truly positive by comparing true positives with all positive predictions. The output first shows the Scikit-Learn version to support compatibility and reproducibility. It then presents the confusion matrix and the counts of true negatives, false positives, false negatives, and true positives to summarize how the model's predictions compare with the actual labels. Finally, it reports accuracy, precision, and recall, giving a concise view of overall correctness, positive prediction quality, and how well the model finds actual positive cases. This script uses Scikit-Learn to evaluate a simple fraud detection model with a confusion matrix. By comparing true labels with predictions, it shows true negatives, false positives, false negatives, and true positives. It also reports accuracy, precision, and recall, helping summarize how well the model performs overall and how effectively it identifies fraud. ROC AUC. ROC AUC measures how well a model separates positive from negative cases across all decision thresholds. It summarizes the ROC curve, which compares the true positive rate with the false positive rate into one score. A value near 1 means strong ranking performance, while a value near 1/2 suggests random guessing. A value below 1/2 may indicate reversed predictions or a problem with how the classes are defined. ROC AUC measures how well a model ranks cases by risk without depending on one fixed threshold, which makes it useful for comparing models. In areas like medical screening or fraud detection, it helps decide which cases should be prioritized before choosing an operating threshold. However, it is not the same as accuracy and does not show the exact number of false alarms or missed cases at any specific threshold. It summarizes ranking quality, not full real-world performance. ROC AUC is useful, but it must be interpreted in context, especially when classes are imbalanced or error costs differ. In rare event problems, a model can have a strong ROC AUC, yet still produce many false positives at practical thresholds because negatives are so common. For this reason, ROC AUC should be considered alongside precision, recall, and calibration to judge whether the model's predictions fit real-world needs. Python code, ROC AUC. This example shows how ROC AUC evaluates a classification model by measuring how well it ranks cases across many decision thresholds. The curve provides a visual sense of how clearly the model separates the classes. We begin by importing key Python tools for data analysis and machine learning. NumPy supports numerical work with arrays and matrices. Matplotlib helps create visualizations, and Scikit-Learn provides tools for modeling. We also load Scikit-Learn's built-in breast cancer dataset, which is commonly used for binary classification. We import the main Scikit-Learn tools needed to build and evaluate a binary classifier. Logistic regression provides the model, while train test splitting lets us evaluate it on unseen data. A pipeline combines feature scaling with model fitting, using standard scaling to normalize the inputs and help the model converge. ROC curve display and ROC AUC scoring are used to assess classifier performance across thresholds and summarize its ranking ability. We load Scikit-Learn's built-in breast cancer dataset, a common dataset for binary classification. The input features are separated from the target labels, which identify each sample's class. This prepares the data for later processing and model training. The code first checks how many distinct classes are in the target data. Because the ROC AUC example requires a binary classification problem, it only continues if there are exactly 2 classes. If not, it raises an error to show that the dataset is not suitable for this demonstration. We split the data into training and testing sets, so the model is evaluated on examples it has not seen before. Using Scikit-Learn's train test split function, 30% of the data is reserved for testing. Stratifying by the target keeps the class balance consistent across both sets, and a fixed random state makes the split reproducible. We build a machine learning pipeline that first standardizes the features, then trains a logistic regression model. Scaling gives the features a mean of 0 and a standard deviation of 1, which helps logistic regression work reliably. The model is configured for enough training iterations and reproducible results, then fitted to the training data to learn the link between features and target labels. To evaluate the model, we first use predicted probabilities to get each test sample's score for the positive class. We can also produce hard class labels using the default decision threshold, but the ROC AUC score is computed from the true labels and the positive class scores. This metric shows how well the model ranks positive cases above negative ones across different thresholds, giving a richer evaluation than hard labels alone. The code compares ROC AUC scores computed in 2 ways, from predicted probabilities and from hard class labels. The probability-based score is more informative because it measures how well the model ranks positive cases above negative ones, while the hard label score ignores threshold information. It also prints the Scikit-Learn version to support reproducibility. We create a plotting canvas with matplotlib, then use Scikit-Learn's ROC curve display to draw the receiver operating characteristic curve. It compares the test labels with the model's positive class scores, showing how performance changes across classification thresholds. The ROC plot includes a dashed diagonal reference line to show the performance expected from random guessing. This gives a baseline for judging the logistic regression model. The plot is titled clearly, includes a legend in the lower right, and is then displayed so the model's performance can be visually assessed. This script shows how to evaluate a binary classifier with ROC AUC using the breast cancer dataset. It trains a scaled logistic regression model, predicts positive class probabilities on unseen test data, and uses them to measure how well the model ranks positive cases above negative ones across thresholds. It also compares this with ROC AUC from hard class labels, which is usually lower because threshold information is lost. Finally, the ROC curve and a random guessing reference line illustrate the trade-off between true positive and false positive rates, and the model's overall ability to separate the 2 classes. Probability metrics. Precision recall curves. Precision recall curves show how a classifier performs as its decision threshold changes, especially when positives are rare or costly to miss. Precision tells how many predicted positives are truly positive, while recall tells how many actual positives the model finds. In settings like medical screening, the curve helps balance catching true cases with limiting false alarms, giving a fuller view than any single threshold. Precision recall curves are especially useful for imbalanced classification because they focus on performance for the positive class. In cases like fraud detection, they show whether gaining more recall creates too many false alerts. A strong model keeps precision high as recall increases, rather than dropping quickly. The overall area under the curve is helpful, but the curve itself should be checked because models with similar scores can behave differently in important ranges. Precision recall curves can be used in multiclass and multilabel classification by treating each class or label as the positive case and evaluating it separately or in combination. This helps show how well a system identifies categories such as bicycles, buses, or labels like jazz and instrumental. Because some classes are easier to detect than others, the curves must be interpreted carefully. They also connect to ranking, since changing the threshold is like moving through a ranked list to see how many high-confidence results remain reliable. Python code, precision recall curves. Use precision recall curves to evaluate models when positive cases are rare. Compare different decision thresholds using logistic regression probabilities. Show the trade-off between precision and recall, and report the average precision as a summary measure. This setup imports the main tools needed to build and evaluate a classification model. It uses NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn to create a synthetic dataset, split it into training and testing data, train a logistic regression model, and measure performance with average precision and precision recall results. We create a small, imbalanced binary classification dataset with Scikit-Learn's make classification function. It has 1,200 samples, 8 features, and 4 informative features that help determine the target. The class split is 90% to 10%, with a fixed random state for reproducible results. This setup models cases where one class is much rarer, making it useful for studying precision recall trade-offs. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function, with 35% reserved for testing. Stratifying by the target keeps the class proportions, including the rare positive class, similar in both sets. A fixed random state makes the split reproducible each time the code runs. Check the test labels to confirm that both classes are present before evaluating the model. If the set of unique labels does not contain exactly 2 classes, raise an error because one class is missing. This prevents invalid evaluation and ensures performance is measured on both positive and negative examples. We train a logistic regression model on the training data, using a fixed random state for reproducibility and enough iterations to support convergence. This model is useful because it produces probability estimates, which allow precision and recall to be evaluated at different decision thresholds. Use the logistic regression model to estimate the positive class probability for each test example, giving each one a ranking score. Then compare these scores with the true labels to build the precision recall curve, which shows how precision and recall change across thresholds. The average precision score summarizes this curve as one measure of how well the model balances precision and recall. We compare 2 classification thresholds for a logistic regression model, a strict threshold of 70% and a permissive threshold of 20%. Predictions are labeled positive when their positive class probability meets or exceeds the chosen threshold. Using both thresholds lets us see how stricter or looser classification changes the model's precision and recall. For the strict threshold, precision is found by counting true positives, where both the prediction and actual label are positive, and dividing by the number of positive predictions while avoiding division by 0. Recall uses the same true positive count, but divides by the total number of actual positives. Together, these measures show how accurate the positive predictions are and how many real positive cases were correctly identified. Permissive precision measures how many permissive positive predictions are actually positive, using a safeguard to avoid division by zero. Permissive recall uses the same count of correct positive predictions, but divides it by the total number of actual positives in the test set. Together, these values show how accurately and completely the permissive threshold identifies the positive class. The output checks the Scikit-Learn version for reproducibility, then reports the positive class rate in the test set to show class imbalance. It also gives the average precision score, which summarizes performance across thresholds. Finally, it compares precision and recall at a strict threshold of 0.7 and a permissive threshold of 0.2, showing how higher thresholds tend to favor precision, while lower thresholds tend to favor recall. This plot shows the precision recall curve for a logistic regression model. Precision is plotted against recall to illustrate how the two metrics trade off across different thresholds. The graph is labeled with a clear title, axis names, standard 0 to 1 limits, and a legend, so the curve can be interpreted easily. This script shows how to evaluate logistic regression on an imbalanced dataset, where positive cases are rare. It trains the model, predicts test probabilities, and uses them to build a precision recall curve and compute the average precision score. It also compares strict and permissive decision thresholds, showing that higher thresholds usually improve precision but reduce recall, while lower thresholds do the opposite. The curve helps choose a threshold that matches the desired balance between finding positives and avoiding false alarms. Log loss Brier. Log loss measures both whether a classifier chooses the right class and how accurate its confidence is. This is especially useful in multiclass problems where probability must be divided among several possible outcomes. It rewards high confidence when the prediction is correct and penalizes high confidence when it is wrong, making it important for tasks like medical triage, risk scoring, and fraud detection. The Brier score measures how accurate predicted probabilities are by averaging the squared difference between predictions and actual outcomes. In binary tasks, it compares the predicted chance of an event with whether it happened. And in multiclass tasks, it compares the full predicted distribution with the true class. It also reflects calibration, so probabilities should match real-world frequencies, such as an 80% prediction being correct about 80% of the time. Log loss and the Brier score evaluate how reliable a model's predicted probabilities are, not just whether its labels are correct. They are especially useful in multiclass, multilabel, ranking, and top K settings, where good probability estimates affect which results are trusted. Log loss strongly penalizes confident wrong predictions, while the Brier score gives a more direct measure of probability error. Python code, log loss, Brier. For multiclass probability predictions, log loss and Brier score evaluate different aspects of accuracy. Log loss heavily penalizes predictions that are confidently wrong, while the Brier score measures the squared error between predicted probabilities and the true outcome. This setup imports the main tools needed to build and evaluate a logistic regression classifier on the Iris dataset. It uses NumPy for numerical work, Scikit-Learn for machine learning utilities, and the Iris data as a standard classification example. It also brings in tools to split the data into training and testing sets, train the model, measure probability-based performance with log loss, and convert class labels into a binary format for evaluation. We load the built-in Iris dataset from Scikit-Learn as a simple example for multiclass classification. The flower measurements serve as the input features, and the species labels serve as the targets. Together, these provide the data needed to train and evaluate a classification model. Use NumPy's unique function to find the distinct class labels in the target data, then confirm there are exactly 3. If the dataset has any other number of classes, raise an error, because this lesson is designed for a 3-class multiclass problem. We divide the data into training and testing sets, keeping 30% for testing. Stratification preserves the same class balance in both sets, and a fixed random state makes the split reproducible. We create a logistic regression model with enough iterations to help it converge, and a fixed random state, so the results are reproducible. The model is then trained on the training features and labels, allowing it to learn patterns that connect inputs to target classes and predict probabilities for new data. The logistic regression model predicts class probabilities for each test sample, producing a probability table with 1 row per sample and 1 column per class. The output is then checked to make sure the number of probability columns matches the number of unique class labels. If not, an error is raised to catch an inconsistency in the model's class predictions. A copy of the predicted probabilities is modified to simulate a model that is confidently wrong. All probabilities are first set to a small value, then each sample is assigned an incorrect class by shifting its true label to a different class. That wrong class is given a high probability, making the model appear highly confident in its incorrect prediction. The true labels are first converted into one hot encoded form, so they can be compared with predicted class probabilities. The Brier score is then found by measuring the squared differences between the probabilities and the true label vectors, summing across classes for each sample, and averaging the result. The same calculation is applied to deliberately incorrect probabilities, allowing us to compare how well the model's probabilities match the true labels against a clearly wrong set of predictions. Log loss is used to compare predicted probabilities with the true labels and measure how well a model's confidence matches actual outcomes. By also testing deliberately wrong, overconfident probabilities, we see that log loss gives much larger penalties to confident mistakes. The output first shows the Scikit-Learn version to support reproducibility, then compares two probability-based evaluation metrics. Log loss measures classifier accuracy and strongly penalizes confident wrong predictions, while the Brier score measures the average squared gap between predicted probabilities and true outcomes. By reporting both metrics for the model and for deliberately overconfident incorrect predictions, the comparison shows how misplaced confidence worsens each score. This script trains a logistic regression model on the iris dataset and evaluates its predicted probabilities using log loss and the Brier score. It then compares these results with deliberately wrong, overconfident probabilities. Both metrics get worse for the incorrect predictions, but log loss rises especially sharply, showing that it strongly penalizes confident mistakes. Multilabel top K. In multilabel top K evaluation, one example can have several correct labels, and the model ranks possible labels rather than choosing only one. The metric checks whether the true labels appear among the top-ranked predictions, where K is the number of labels considered. This is useful when the goal is to help people review prioritized options, such as likely medical conditions, music genres, or moderation categories. Top K evaluation measures how well a model ranks labels, rather than only whether their probabilities pass a threshold. In multilabel classification, this matters because several labels may be relevant, rare, or overlapping. A strong model places the correct labels near the top of its ranked list, which is especially important when only a few recommendations or suggestions are shown. When interpreting multilabel top K results, the key is choosing a K value that fits the task. Smaller values make evaluation stricter, while larger values may improve scores, but can give users too many labels. The right choice depends on the application and the number of true labels expected. Because annotations may be incomplete, top K metrics should be judged alongside other measures and domain knowledge. Python code. Multilabel top K. This section demonstrates multilabel top K evaluation by comparing a model's ranked predictions with the true labels. It shows how recall changes as K increases or decreases, helping assess how many correct labels appear among the top predictions. We import NumPy for efficient numerical calculations and array handling, and use Scikit-Learn for machine learning utilities. From Scikit-Learn's metrics tools, we bring in the top K accuracy score function to evaluate whether the correct label appears among the model's top predictions. We define category names such as dog, bike, tree, person, and car, so numerical labels can be interpreted clearly. The true labels are stored in a two-dimensional structure, where each row represents one instance, and each value shows whether a category is present or absent. This supports multi-label classification, where a single instance can belong to more than one category. A NumPy array stores predicted probabilities for labels across multiple instances. Each row represents one instance, and each column gives the model's probability for a specific label. This structure makes it easy to compare predictions with the true labels and evaluate model performance. The code first verifies that the true labels and prediction scores have matching shapes, so each score lines up with one label. If they do not match, it raises an error to indicate inconsistent input. This check helps prevent later calculations from using misaligned data. The code first displays the Scikit-Learn version to help confirm compatibility and available features. It then shows the true labels for the first example in readable form by listing the label names that are marked as correct. This helps verify the data and clarify what the model is expected to predict. The process evaluates multi-label top K recall for K values of 1, 2, and 3. For each value, it finds the highest scoring predictions in each row, checks how many of their labels are truly correct, and compares that count with the total number of true labels. The average of these ratios gives the recall for that K, which is then printed rounded to 3 decimal places to show how well the model's top predictions match the true labels. The correct class index for each row is used to evaluate single-label top K accuracy. Scikit-Learn's top K accuracy score then checks whether the true class appears among the top 2 predicted scores, using 5 possible labels. The final result is printed as the single-label top 2 accuracy, rounded to 3 decimal places. This script shows how to evaluate classification models using top K metrics. For multi-label data, it compares true labels with predicted scores and computes average recall for different values of K, showing that recall usually increases as more top predictions are considered. It also demonstrates Scikit-Learn's top K accuracy score for single-label classification, measuring whether the correct label appears among the top 2 predictions. Overall, it illustrates how changing K affects performance evaluation. In this lecture, you learned to use built-in and custom scorers for classification evaluation, compute and interpret threshold-based and probability-based classification metrics, and evaluate multiclass, multilabel, ranking, and top K classification outputs. In the next lecture, Lecture B, we will go over regression clustering.
Thank you for your attention. See you all in the next lecture.